So thank you very much. It's very nice to be here. This is my first visit to Mainz, hopefully not the last one. These lectures should really be given more in the second or third week, not the first one. The fact that in the first one is entirely my fault, not the organizers, just my schedule. But I appreciate that they were accommodating, and also that you are accommodating, that we have them in the first week. So I'm going to talk about dark sectors. And principally, we'll cover a lot of different topics here, so I'm going to be selective a little bit. Hopefully, you'll get something out of them. Just before I start, I want to get to know my audience a little bit. So who among the participants is already a postdoc? Okay, so among the participants, so no one, okay, good. So who is going to apply for jobs, for postdoc jobs in the fall this year, in upcoming fall? Okay, so only 2 of you. Okay, so who is going to apply next year? Okay, and then I guess everyone else, the younger, or you're just not even going to apply ever? Okay. Okay, so who knows about dark matter? Okay, there's lots of this stuff going on. Okay, who works on dark matter? Okay. Who knows what a dark sector is? Yeah. Okay, and who works on dark sectors? I guess maybe there's a strong correlation between those things. Okay, so not that many. Okay, so what I want to do, so there's no lectures at the schools on dark matter, so I want to begin in a few minutes on the dark matter landscape. So I'll spend some time on this, not directly dark sectors, but it's sort of all related to try and put everything in a slightly bigger context. I'll mention WIMPs briefly, and then we'll talk about dark sectors, why I want to particularly focus on dark sectors below the GeV scale. We'll talk about accelerator-based searches, how to find them at colliders, at beam dumps, and at LHC, things like that. And then we'll talk about new direct detection techniques for very light dark matter below the usual WIMP scale. And then, if there's time, depending on how much time there's at the end, we'll try to put everything together, talk a little bit about models, more specific models and projections for the next decade of what we hope to achieve. So, when I was preparing these lectures, I was thinking back to when I was about your age or your time scale. So when I was transitioning from PhD to postdoc, so that was about 10 years ago, or exactly 10 years ago in the summer. And it was a very exciting time. The LHC was about to turn on in September of that year. There was tons of anomalies floating around that were related to dark matter. Dama is still around, but maybe less interesting now. There was the WMAP haze, there was Attic, there was Pamela, which saw a big cosmic ray positron access. Who knows about these things? Pamela, Attic, some of you, very few. Okay, shows my age maybe. But it was a very exciting time because we're thinking about possible dark matter related anomalies. So DAMA is a dark matter experiment that sees an annual modulation in the signal rate. It's an experiment that gets put deep underground. They look for dark matter scattering of nuclei, and they see a modulation, which is what you expect because the Earth goes around the sun. So every year, the rate of how many dark matter particles you intersect actually changes as a function of the time in the year, and they see that signal. And then we also saw a big cosmic ray excess in positrons up to 100 GeV, which was suggestive of dark matter annihilating to positrons, giving you some excess. So there are lots of signals around. 10 years later, the LHC has turned on. It's been very successful in finding the Higgs boson, but it's been a little bit disappointing from a new physics point of view of finding other things as of yet. A lot of the anomalies have gone, and the time is sort of a little bit different now. And back then, I think we expected this huge deluge of data coming towards us, right? There was lots of excitement. We want to find out what solves the Higgs hierarchy problem, find supersymmetry maybe, find dark matter, things like that. Now I think things are a little bit different. We still actually have a lot of data coming. The LHC has really just ran a tiny fraction for its entire lifetime, right? We have a ton more data coming from the LHC, and who knows what we're going to find. There's more dark matter experiments coming, but the experiments are getting big, also the dark matter experiments. But at the same time, in 2008, this idea of a dark sector really started taking off. Okay, and I'm not going to motivate the historical perspective from that, but it sort of really started taking off in around 2008. They were, of course, known well before then as well. Dark sectors have been around for ages. especially depending on how you define them. Lots of things are a dark sector. But around 2008, motivated in part by these anomalies, the idea of a dark sector became much more mainstream. And now, today, there's a lot of different theorists, young theorists, postdocs, even grad students, coming up with new ideas for experiments, new ideas for what else we should look for dark matter. And it's sort of a very exciting time because we have this different set of little small-scale experiments that are starting up. And I'll tell you a little bit about them, or new analyses with existing experiment that people haven't thought about before, that were starting up back then. And there's actually a very exciting time, I think, right now in particle physics. There's a lot of activity in coming up with new ideas to look for different things, not just at the weak scale, but especially for light dark matter. And I'll try and give you a glimpse of that in these lectures. So, good reference, I think, for these lectures. So there's many references that I'll give throughout the lectures, and they'll be incomplete. But there's a workshop that took place last year in the United States, which was called Cosmic Visions Workshop. And there was a community white paper written about this, and it actually serves as I think, a good summary of some part of the field. The year before, there was a workshop at SLAC called Dark Sectors Workshop. And again, there was a summary paper written. And I'll just give you the archive number for this as well. And what these things do, these papers do, they talk about the motivation for dark sectors. They talk about what kinds of things we could be looking for, and especially focus on new experiments, new small-scale experiments that could be done over the next decade or so that could look for this. And there's other things. So another community report. And then I'll give references in lectures. Incomplete, I'm sure. But nevertheless, I'll try and do that. Okay. So I think to start, actually before I start with the dark matter landscape, in terms of evidence for new physics, what evidence for new physics do we have? Throw some stuff at me. Yeah. Neutrinos? Yeah. Okay, so sterile neutrinos. Okay, so there's anomalies in data. Okay. Mm-hmm. Matter-antimatter symmetry. Okay, that's an observational fact. Okay, so that's a big thing. That's different from the anomaly. Okay, so this is something that really requires new physics. Matter-antimatter asymmetry. What else?
Hubble parameter. Tension in the Hubble parameter.
That's an anomaly. Okay. So yeah, well, why does the Planck measurement of that doesn't quite conform with the low redshift stuff? Yeah, low redshift measurements. Okay, what else? But that's again an anomaly. That's not really required. Give me stronger evidence. That was one strong thing. Yeah.
Large-scale formation structures.
What's the problem?
Well, when we calculated it, we didn't have that matter. Then the structure formation would have taken place completely differently if there was only baryonic matter.
So that's evidence for dark matter.
Yes.
Right. So dark matter. There's tons of evidence for dark matter. That's one example that you gave. The CMB gives very strong evidence for the existence of dark matter. Rotation curves. So dark matter. That's another very good thing. Yeah.
I was just going to get the rotation curves.
Yeah. So that's all basically related for dark matter. Okay. So dark matter and matter-antibaryonic symmetry. Those are strong pieces of evidence for new physics. Massive neutrinos. Yes, that as well. Okay, so we've got dark matter. We have baryon or matter-antimatter symmetry. The writing is big enough for the back? Yeah? Okay, please complain if it is not. Okay, and what else? And someone said, I'm sorry, did you say, yeah, neutrino masses, yeah. Okay, neutrino masses. So those are really strong pieces of evidence for new physics beyond the standard model. There's other things like anomalies which we've already heard, and then there's also things which are sort of conceptual mysteries or hints, like what? Like what other things are sort of not satisfactory? Naturalness, very good. Okay, so let me put this a little dash line. So naturalness, you'll have one of the world's experts talking about this, Nathaniel, starting next after me. Okay. Higher, that's related, yeah. Okay. Depending what nationals you meant, but so I thought about Higgs. I thought that's what you meant, yeah. Okay, what else? Okay. So there's, for example, the strong CP problem. Okay, why doesn't the strong force violate CP much more than is observed to be? And Nathaniel's also going to talk about this. Yeah. So that's why. So here I meant. Thank you. Fine. Higgs hierarchy. That's what I thought you meant when you said it, but I guess I was wrong. Okay, good. So good. So so those two things. What else? Flavor. Flavor universality, yeah, and fermion masses, the mass spectrum of fermions, why is it so different, these kind of things, okay? So, fermion masses, and flavor puzzle. And there's other things which, there's another national thing is, of course, also the cosmological constant problem. Nathaniel, I don't know if you'll talk about that, but you will? Okay, very good. So let me just add this here. Fine, I'll do the following. 1, 2, and this might get too small, but that's okay. CC, cosmological constant, okay. Fermi masses and flavor puzzle. There's things like, inflation, okay. There is grand unification of the forces that we have actually unify in the grand unified theory. There's some evidence, of course, for that, but we don't know for sure. And then, and there's anomalies. So let me just write down inflation and then stop. And then there's anomalies, which I won't write down all of them. There's quite a few, and they're interesting to varying degrees. But anomalies are useful, even if they go away. They're actually very useful because they motivate you to think about what other physics might be out there, and then often will have ripple effects of making you think about other things. That's what happened in 2008, I think, where a lot of these anomalies largely, I think, went away, but the idea of a light dark sector really came to the fore back then. Okay. Now, many of these things can be addressed by a dark sector. Okay. So I won't discuss this in detail, but I'll focus on dark matter. But I think the fact of all the evidence for dark matter is strong motivation to look at dark sectors, because we don't know what dark matter is. And I'm not going to review the evidence here, but the seeming fact that we have a particle out there that doesn't seem to interact very strongly with the standard model, either electromagnetically or through the strong force or the weak force. Possibly the weak force that could still be true, but it doesn't seem to interact very strongly. That suggests that dark sectors are something useful to think about. Okay, that there's some sector out there that interacts at least gravitationally with us, and of course to make it interesting from a laboratory point of view. So you just have a dark sector that does only interacts gravitation, then we can try and study this with galaxy structure formation or some gravitational probe, like with Gaia or something. But what we want to if we want to have laboratory probes, we need something more. We need some additional interaction between the dark sector and the standard model sector. And there's a few interesting things that are worth thinking about, and I'll talk about that. But to make it interesting, we want some connection to the standard model. And a lot of these things can be explained with the dark sector. Okay. And then one other general comment. So that's evidence for new physics. So in terms of what could this new physics be? Okay, possibilities for new physics. So very generically, we could have some very heavy state, okay, that is charged under the standard model. With a mass much bigger than the weak scale. so order 100 GeV. The way we look for that, how do we look for that? Direct searches? So I mean much, much heavier. So what direct search? So make it 100 TeV, 10 TeV. Above the LHC. Right, so is there any way to look for that? Precision measurements, so indirectly. Okay, so rare decays, so rare decays, or rare processes in general, and precision measurements. So then we can have states that are charged under the Standard Model with a mass that's of order the weak scale. And then, of course, we have collider probes, okay, like LHC, etc. And then what we can also have is we can have very light states. But in order to ensure that generically, in order to ensure that they're not things we would have seen, we have to make them neutral. Okay, so gauge singlets. So the mass of the gauge singlets can be a lot less than the weak scale. The reason we didn't see them is because they don't interact much with the Standard Model matter. But what we can still do is we can still have precision measurements, high intensity measurements, high intensity beams that we can collide and look for these states. They're rare processes, but they can still happen. As long, of course, again, the caveat, and that's the thing that makes it interesting, is if there's a connection to the Standard Model. Okay. Otherwise, there's no point in these searches. Okay. So we can have high intensity precision measurements. And this is what I'll talk about a little bit in the with accelerator-based probes. Okay.
Question?
Yeah.
The gauge singlet under which gauge group?
All of them. Complete Standard Model gauge singlet, yeah. Okay. And very generically, right, in terms of what's allowed, if we have mass here and coupling to the Standard Model of some new state, then for heavier masses, larger couplings are excluded, and for lighter masses, you can probe smaller couplings. Okay, so very generically, as a function of from a coupling of Standard Model to as a function of the mass of some new particle that you might be interested in, very roughly the bound looks like this. Okay, and of course I'll show something more precise as we go along. But for very high masses, that's what you want to look with high energy colliders like the LHC. And for lower masses, you want to look for this with high intensity. And precision. And these dark matter searches that I'll talk about, so direct detection of dark matter, even for WIMPs, of course, they are searching for very, very rare processes. They've reached amazing sensitivity, for WIMP dark matter, where you are sensitive to, order 1 interaction per ton per year. Okay. So of material. Okay. So those are also precision measurements, if you like, precision searches. Okay. Okay. So after this very generic thing, any questions?
So this assumption that you don't couple to the Standard Model, that's just to make it convenient, or?
That's so that I can give these lectures in dark sectors.
Yeah.
So that's what by definition what a dark sector would be, right? So if you want to have new states at low mass, generically they cannot couple directly to the standard model. Okay, generic statement. I'm not. Yeah. But the way to make them still viable is if they just don't interact with the standard model. But there's other interactions that exist, and I'll give you examples. Okay. Yeah.
And the reason is because we've been smashing standard model particles together for a long, long time, and we haven't seen any of these.
Right. Okay. Okay. So now let me talk about the dark matter landscape. And I need a board that's long. I can erase this, right? Everything's good. Okay, so the question is, what do we actually know about dark matter? Going from very generic assumptions, minimal assumptions, to more detailed things. So let's do a brief review of the landscape of dark matter. So what I want to do is, I want to show you the mass range where dark matter could be. So this is the mass. Okay. At the low end, there's roughly 10 to the minus 21 eV. Let me go a bit higher. Somewhere there's M Planck, and somewhere there's 100 solar masses. And very roughly, we know that dark matter has to be somewhere in this mass range. Okay? So this is good news, right? So we know something. It can't be anywhere. Okay. So that's good. But let's talk a little bit about where these mass ranges come from. Okay. So at the very lowest end, what we have is that if you're a boson, and you're the dark matter, you need to be above this mass range, 10 to the minus 21 eV. So where's that coming from? Let's talk about that. So I'll fill in scales as we go along. Okay. So so I'll try and number these, and then I'm going to try and let me keep this board clean, and I'll just start here again. And what I'll do for the next few minutes is I'll just give you rough estimates, okay? All these can be made more precise, but I just want to give you rough order of magnitude estimates. So let's imagine you have a boson, okay? So then it has a de Broglie wavelength. And what you want, and the de Broglie wavelength is given by lambda going as h over p, where p is the momentum of the particle. So we know that we have things called dwarf galaxies. So dwarf galaxies are small galaxies. So Milky Way is 10 to the 12 solar mass or so. Dwarf galaxies can be much smaller, down to the 10 to the 8, 10 to the 7 solar masses. And the Milky Way galaxy, the visible part of the Milky Way, the baryons, the disk, how big is that?
15 kiloparsecs.
In radius?
Diameter.
Yeah,
15
bit more.
kiloparsecs.
Bit more. 30 kiloparsec in diameter. Okay, so what's a parsec? Let's see. So 3.26 light years. Okay, a parsec. So here's the center of the galaxy. The sun is here. The distance from us to the center of the galaxy is about 8.5 kiloparsec. Parsec is 3.26 light years, and a kilo is 1,000 times that. And we're about 8.5 kiloparsec away from the galaxy center, okay, the sun. The whole disk is about 30 kiloparsec, 100,000 light years. But the dark matter halo, where we think the dark matter lies, is about a factor of 10 times larger than this. Okay. So the dark matter halo, we're in a big dark matter halo that's about 300 or so kiloparsec diameter. Okay, and within this halo, there's of course other structure. There's dwarf galaxies. So we see other small galaxies in it, like dwarf spheroidal galaxies. Draco is an example. Segway 1, Segway. There's probably other Segways. There's many little dwarf galaxies, and they orbit our galaxy as well. But at the very least, we know we have dwarf galaxies, and their size is about a kiloparsec.
So what is the size of the halo based on? Like, where do we get that?
So we would say, when does it stop become gravitationally bound, right? So that's one way to define a halo. Okay. So very roughly, I'm just giving you rough numbers, right? It's about 300, so 10 times larger than the visible stuff. Okay. The largest gravitational bound objects in the universe are galaxy clusters, which are collections of galaxies, okay, which are much larger than our Milky Way galaxy. So they would be like in a galaxy cluster. Okay, so you have clusters of galaxies as well. But what we have are dwarf galaxies, and we know those exist. And if dark matter, and we know they're dark matter dominated, so these consist of mostly dark matter. And if dark matter has a de Broglie wavelength that's larger than the size of the dwarf galaxy, then they couldn't really exist. You can't really form structure smaller than the de Broglie wavelength. Okay, so we can estimate what the de Broglie wavelength is before it's about a kiloparsec. So let's do that very briefly. So a dwarf galaxy has a size of about a kiloparsec. The velocity of the dark matter in the dwarf galaxy is of order 10 kilometers per second. Okay, what's the dark matter velocity in our halo here, in the big Milky Way halo? I heard something which sounded right, but who said it?
200 kilometers?
Yeah, 200, yeah, roughly, okay? So a few hundred kilometers per second, okay? The largest velocity of dark matter in the halo, so there's a largest velocity because if the velocity is too large, it would escape. So there's some escape velocity. It would escape, it would not be gravitationally bound. That's about 600 kilometers per second, okay? So, but about 10 to the minus 3 times the speed of light, 300 kilometers per second. That's roughly the velocity of the dark matter in our halo. In a dwarf galaxy, they are less massive. A dwarf galaxy is its own bound system, which is orbiting within within our galaxy, for example, or other galaxies. And they, because they're smaller, their velocity has to be smaller as well. And it's about 10 kilometers per second. Okay. So, so if we want lambda to be a kiloparsec, so you can do these numbers by yourself, then what we need, so momentum is just mv, so what we get is that m is h over lambda v, and we want this to, and if we put in Planck's constant, this velocity, and the lambda over kiloparsec, what we find is about 10 to the minus 21 eV. Okay, and I'll use natural units, okay, mostly, except there, or whatever, okay, or there, keep going.
How do we find this velocity?
So you can measure it. So you can look at the stars inside a dwarf galaxy, and you just do, you can just look at the Doppler shifts, see how they move, and what you find is a dispersion of order, 10 kilometers per second.
But aren't you interested in the velocity of dark matter, not just the...
Okay, good question, sorry. So that's the stars, you're right. But that gives you actually an idea of how much mass there is, right? And then basically, the sun is orbiting at a few hundred kilometers per second around the galactic center. But everything within the same potential, right? So if there's dark matter, that's the same kind of velocity that it has to have, of the same order. Okay. Yeah, thanks. Does that answer the question? Yeah. Okay. Right, so dark matter, right, all of the stuff is inferred from baryons, right? We look at stellar motions, we look at baryons, and basically infer the presence of dark matter. Okay. And in our Milky Way, there's more dark matter, the velocities are higher, or in other galaxies, the velocities are higher than you would expect them to be if the only matter that there was is the baryons. So there has to be more stuff, which is what we think is the dark matter. That's one piece of evidence for dark matter. Okay, so very roughly we get this, and And that's the rough lower bound. So if you make it smaller, if you make this thing smaller, the mass, if you make the mass smaller, the lambda will be larger, and you would get in trouble. And dark matter around this mass scale is often referred to as fuzzy dark matter. So dark matter near and there's strong constraints on it, like to be around exactly there. There's, for example, constraints from Lyman alpha forests, etc. And let me just give you a reference. 1703, 04683. Okay. Something called Lyman alpha, which I won't explain. But those are set constraints on low mass dark matter. Okay. So now we can do the same thing for fermions. And very roughly what we'll find is that fermions will have a bound of about a keV. Okay. So let me put keV here. Okay, and let's quickly do that. So for fermions, of course, you can't, you've got the Pauli exclusion principle, so you can't pack as much dark matter into a small size as you could for a boson. And what we can do is derive a bound, again from the existence of dwarf galaxies, on fermionic dark matter. Okay? And just to give you an order of magnitude estimate again, so rough lower bound on fermionic dark matter. So, so there's various ways of doing this, and some more precise than others, or one can do this more precisely. So here's a rough estimate. So let's say we've got some halo of dark matter, like the dwarf galaxies that we talked about, or our Milky Way halo, and it's made up entirely of some fermionic dark matter with a mass mf. Then the mass of the halo is going to be given by this mf times the volume of the halo, so just the size of the halo, times the integral over the distribution function of integrated over all momenta. So this f of p tells you how the dark matter is distributed, okay, in momentum. And what we know is that you can't pack in more dark matter than the Pauli exclusion principle allows. So for example, for your spin half particle, you can put two states, some g. So for fermion, this g, or let me call it f actually, sorry. It's 2, and this has, so this entire thing, the mass of the halo has to be less than gf mf v integral of d3p. Okay, so the distribution, you can't have more than two particles per state, so, or some generically some g. And then what we can do is just very roughly, we can give the momentum, integrate over all momenta. Okay, so this is some momentum cubed that you get. And what we can do is take this to be gf mf v times the dark matter velocity, dark matter mass times the velocity cubed. Okay, so just some tilde. Okay, and the volume of the volume here is the volume of the halo, which goes as some radius of the halo cubed. Okay, we're ignoring 4 pi's over 3 and things like that. Okay. Sorry, say again. This here, sorry, this is mf, so the mass of the fermion, times the volume times the velocity. Thanks. Sorry. Okay, so that's the scaling there. And then what we can do is, again, we can, what we need to do is we need to have an estimate of the velocity. Okay, so the velocity of the dark matter in the halo, again, is basically set by the gravitational potential. And a simple estimate for the velocity is the so-called virial velocity. And the way you derive that is very simple. So you take m times v squared over r to be just the gravitational force. And so the velocity is given by g times the mass of the halo over r. And then we can plug that into this expression. And we can then derive a bound on MF from this inequality here. And what we find is I can fit it in here. Okay. We find is that the mass of the fermion is larger than 1 over g fermion to the 1 over 4th. And then there's a parentheses with factors of g cubed in it, the halo mass, and the radius of the halo cubed. And this is to the power of 1 over 8. Sorry for the equations merging into each other. So this is to the power of 1 over 8. Okay. Okay, so just putting everything together. And then we can put in numbers. So again, let's pretend we have we have the existence of dwarf galaxies. Okay, so we put the mass of the dwarf galaxy in there. We can put the radius of the dwarf galaxy in there. So let's put R halo to be a kiloparsec again. The mass of the halo is about 10 to the 8 solar masses. So again, our Milky Way halo is about 10 to the 12 solar masses with all the dark matter in it. And we just put those numbers in, and what we find is that MF is greater than about 100 eV using these numbers that I gave. Okay. And then, of course, you can do more sophisticated analyses. You can get stricter bounds in principle, but very roughly, it's about a keV or maybe a little bit less. Okay, so I'll just put the error a little bit down. Okay, that's for fermions. Totally generic, doesn't depend on anything. It's just a constraint on particle dark matter. Okay, and so if you look at, want to have some references, so Tremaine, Gunn were the first ones, as far as I know, to use similar arguments. There's a paper by Boyarsky and company where they do this more sophisticated than what I presented it here. There's also a paper by Randall, Schultz, and Unwin in 2016. Okay. So these bounds are generic, but and of course you can get more precise bounds if you actually make some additional assumptions, which we'll do now in a minute. But any questions on this? So these are, anyway. Who knew about these bounds, just out of curiosity? Few. Okay. You learned something. Okay. Most of you, not everyone. Whoever put up the hand didn't learn anything, but that's okay. Okay, so so this tells you that if you want to have dark matter below a keV, which is totally fine, right? But it needs to be a boson. Okay, it can be a scalar, it can be a vector boson, it can be pseudoscalar, and there's some great examples of this. So dark photons are a vector, axions or axion-like particles are a pseudoscalar, or you can have some scalar particle, okay, as well. Okay, that's good. And let me just, so there's this joke at the beginning that dark matter has to be somewhere in between. Of course, any particular mass range you pick or any particular dark matter candidate you pick, there's a lot of constraints on things. So when I say, it could be anywhere, that's true, but the other parameter that's important is, of course, also the coupling. How strong does that dark matter candidate interact with the standard model particle? If it interacts very strongly, it's excluded, right? So like axions or scalar particles or vector bosons, dark photons, there are very strong constraints on them from stars. So you can produce these things in stars, and they would cool. If these low mass dark matter particles exist, you can produce them as stars, and they would emit these particles and help the star to cool very quickly in conflict with observations. There's constraints on that. So those are often called stellar cooling constraints. And they exclude lots and lots of parameter space. Okay. And there's many other examples of constraints. But generically, in terms of general bounds, this is what we have so far. Okay. So next. Yeah.
Would the bound on bosons still be valid if we were considering a dark matter candidate which is strongly interacting with itself?
If it interacts strongly with itself.
No. Did you say with itself or with standard model?
With itself.
With itself.
Yeah. So I think this one would, because you still have to get over the de Broglie wavelength, right? So you're saying something will cut off the de Broglie wavelength.
Yeah.
So if you're able to do that, then yes, you can do that. But I don't quite know of a good example of how to do that. Okay. So let me talk about another bound that's sort of important to know about. This KV mass range is sort of interesting because lots of stuff happens around this mass range. So another bound that sits around the KV is the so-called warm dark matter limit, which is around the KV. So let's now make an additional assumption. So not to have a totally generic, but actually make an additional assumption. Let's assume that the dark matter is in thermal equilibrium with the standard model particles in the early universe. Okay. So that assumes that the dark matter interacts with the standard model particles. And if it does, and interacts strongly enough, you can produce the dark matter of the early universe, and the temperature of the dark matter, the dark sector, would have the same temperature as the standard model. And you can just produce it, and the dark matter you can have standard model particles annihilate to dark matter particles, and vice versa, in principle. Okay. So that's a very generic, well, it's less generic than what I've done so far, but it's still a pretty generic assumption. And that's also where the WIMP will come from, as I'll very briefly review in a bit. Okay. So let me just give you some definitions. Right, so just to make sure we're all on the same page. So what we think, there's a lot of evidence for that. So initially what we think is that the universe was very, very hot. Okay, we don't know what temperature it reheated to after inflation, but it was very hot, certainly well above an MeV. Why an MeV? Because that's when BBN started, Big Bang nucleosynthesis. Okay, so that's when neutrinos started decoupling at around a temperature of an MeV, which happened about 1 second after the Big Bang. And then nuclei started to form, after that. But above that, it was even hotter. And as the universe expands, it also cools. Okay. So we have dark matter, and we just divide this into different pieces. So we can call something a hot relic. So relic from a long ago era, I guess that's where the name relic comes from. So hot relic. So this is a particle that decouples from the standard model particles when this particle is still relativistic. Okay. So often the assumption here is that the dark matter and the standard model is in thermal equilibrium in the early universe, maybe chemical equilibrium. Or kinetic equilibrium, but it's an equilibrium, and the velocities of the dark matter are basically set by are relativistic, okay, initially, and then as the universe expands and cools, the dark matter might stop interacting strongly with the standard model sector. The reason being that it expands and cools and dilutes, so you've got less dark matter particles hitting standard model particles, or dark matter particles annihilating to standard model, or vice versa. Just because the universe gets dilute, there's not as much density around. Okay, so when the particle decouples when it's relativistic, we call it a hot relic. And then there's sort of two different regimes. One of them is that the The dark matter that then results could be hot dark matter. This happens when the mass is below 1 electron volt. Or it could be called warm dark matter when the mass is above 1 electron volt. And why 1 electron volt? Why is 1 eV an interesting number? Maybe someone knows some cosmology. Neutrinos decouple at an MeV, 10 to the 6 orders of magnitude higher. Sorry, 6 orders of magnitude higher. Sorry, what did you say?
This is matter radiation equality, right?
Yes, matter radiation equality. Yeah. Is that what you said? I'm sorry, I misunderstood. I heard neutrinos.
Yes, like, yeah.
Okay. Okay. So this is matter radiation equality. It's at this temperature around an EV at which the universe becomes matter dominated and structure can start forming. Before that, the radiation was just dominating and you couldn't really form structure. Everything was too hot. But after an electron volt, when the universe was colder than 1 eV, you could start forming structure. Okay? And if we've got a relativistic particle that decouples when, so a particle that decouples when it's relativistic, it could either be by definition hot if the mass is less than eV, which means that it's still relativistic as structure starts to form, or it could then become, or it would be non-relativistic because its mass would be heavier than eV. So its temperature would then be less than the mass and it becomes non-relativistic. And in which case we call it warm dark matter. Okay. And then we've got the other case, which is a cold relic, which decouples when non-relativistic, and this we call cold dark matter. So this goes out of equilibrium with the standard model when it's cold, when it's non-relativistic, and it's also non-relativistic by the time of matter radiation equality, of course, as well. Okay, because we assume it decouples earlier. So now hot dark matter is excluded. Okay, so a while ago, well, many years ago, people thought that neutrinos could be all the dark matter. The standard model neutrinos could be all the dark matter. Neutrinos are an example of a hot dark matter component. Okay, if you like, neutrinos form a small amount of hot dark matter in our universe today. Why? Well, their mass has to be well less than 1 electron volt, just from oscillation measurements, we know that, and from constraints, okay, on their masses. So, but if neutrinos were all of the dark matter, structure would form very differently than what it's observed to do. Okay, if you had hot dark matter, what you do is you first form large-scale structure, and then it starts breaking up into smaller pieces. Whereas if you've got cold dark matter, it's the other way around. Small stuff forms first, and then you build up into the larger pieces. And the latter is what's observed. But good. Okay, and then there's so neutrinos are an example of hot dark matter. And even though they're not all the dark matter, if you like, they form a small amount of hot dark matter component. Okay, if you call them dark matter. We don't usually because they're in the standard model. Okay. But and if it's warm, so generically that by definition it's 1 electron volt, but it turns out that the actual limit is more like a keV. Okay, 3 orders of magnitude stronger. And the reason again it has to do with structure formation. Okay, that basically if the dark matter is relativistic down to temperatures below a keV, then you wouldn't form dwarf galaxies again. Okay. So I'm wondering if I should go through that argument. Maybe I'll skip that, given the time. Okay, I'm going to skip that argument, but we can talk about it afterwards. But basically, just to sort of summarize and write down some equation, even if I'm not going to explain it much, let me just do that at least. So the warm dark matter limit comes from the idea that the dark matter is free and relativistic for temperatures that lie between the dark matter mass and the time of decoupling or freeze out, Okay, so let me call it with an F here, so decoupling. Let me call it D. Okay, that's the decoupling temperature. And the dark matter will only become non-relativistic once its temperature drops below the mass. Okay, then it actually slow down and become non-relativistic. And if it's relativistic, it can't form structure. Okay, it just moves fast. So you can't really have it fall into overdense regions to start forming structure. It'll just free stream. So it escapes potential wells. Filling in underdense regions. Filling in underdense regions in the universe. And we say that it free streams. So it freely streams all over the place and will not form structure. And this free streaming stops once the temperature of the dark matter reaches the mass. Okay? And then you can start forming structure. But if that is too delayed, then the free streaming is so large that basically you've got a huge region in the universe, so huge patches of regions in the universe where the density is basically smooth, and those can then start collapsing and form structure, but the structure they form are much bigger, would be bigger than dwarf galaxies. Okay. So the longer it free streams, the larger the regions that will then collapse, and if it's too large, then you can't form dwarf galaxies. And very roughly what you get is that the temperature that for a 1 keV dark matter particle, okay, I'll squeeze in here. So for heavier dark matter than 1 keV, you can form structure that's bigger than about 1 kiloparsec. And for lighter dark matter, it's going to be relativistic too long, that it's going to just wash out larger scales, and you can only form 10 kiloparsec or higher. Okay. All right, good. So that's this bound here. So that tells you, okay, if dark matter is in thermal equilibrium with the standard model of the universe, it has to be above a keV. That happens to coincide also with fermions, but the bounds are really totally independent. Okay. And just to be clear, bosons, so above a keV, of course, the dark matter could be either boson or fermion. Okay, so nothing prevents the bosons, of course, to be going past this. All right, good. So then another important scale is the WIMP scale. So let me put some scales here. So let's put an MeV. Clearly, this is not to scale here, but okay, good. All right. So in this mass range here, we have what are called WIMPs between about a GeV and 100 GeV, and I'll explain both those bounds in a few minutes. If dark matter is in thermal equilibrium, it can be anywhere between right here and about 100 TeV. So below this, it's too hot. Okay, that's the warm dark matter mass limit. And above this, there'll be too much of it, as I'll explain in a few minutes now. And good. So let me talk a little bit about WIMPs. Okay, so who's heard about WIMPs? Who's not heard about WIMPs? Maybe that's a better question. Who's shy? This was a binary question. Not everyone put up their hand though. Okay. So I assume most of you have actually then. So, but that's fine. So we'll just say a few things about them. So WIMP stands for weakly interacting massive particle. So this is a particle that's massive, so heavy-ish. So usually people take it around to be around the weak scale, okay, 100 GeV or so. But this is the range that I was indicating where it could be, between roughly GeV to 100 TeV, as we'll see. It's weakly interacting, so different people have different definitions. Some people have different definitions depending on the time of the week. So often what I take is this weakly is the standard model weak force. Okay, so with SU2 cross U1, the electric weak force. Some people take it to be more generic, just some weak force. Okay, so but usually I take it to be the standard model weak force. And this is a great dark matter candidate for several reasons. So one reason is the following. So let me just remind you, who knows about the WIMP miracle, so-called WIMP miracle? Who does not know about it? Okay, good. So let me just say, how much do I want to say? Okay, so let me just briefly say some things. Okay, so let's imagine that we've got some dark matter particle, let me call it now chi, lying in standard model particles in the early universe. Through some process, there's some box here which I'm not specifying. Okay, it could be with a standard model weak force. Yes, Michael, you're correcting me. Say again? That's right, yeah. Yeah, I didn't invent the name, and I said so-called. Yeah, so it's maybe not a good name, but yeah, good. Okay, so dark matter particles. The assumption here is that dark matter particles annihilate to standard model particles in the early universe, and vice versa. So this process can go both ways in the early universe. So this assumes some interaction, obviously, okay? And it means that the standard model and the dark matter are in thermal equilibrium in the early universe, okay, and chemical equilibrium. And what we can do is we can plot the number abundance as a function of, let me plot it as a function of time, very generically. And this is the abundance of dark matter. And the early universe, the abundance of dark matter will scale as the temperature of the universe cubed when the dark matter is relativistic. And it's going to scale as an exponential when it's non-relativistic. And the assumption here about WIMPs is that they will decouple when they become after they've become non-relativistic. Okay. So if we plot this abundance, what happens, and this is assuming thermal equilibrium, all these things. So these expressions just come from Bose-Einstein or Fermi-Dirac statistics, just statistical distribution functions. You can just calculate the number abundance. When it's relativistic, it goes as t cubed. When it's non-relativistic, it becomes basically a Boltzmann equation, and it's going to be some exponential that's suppressed. Okay. But as the time goes up, as the universe expands, as time evolves, the temperature of the universe drops, and the temperature, right? So the temperature drops, and what you basically get is that the abundance of dark matter is going to be slowly changing as it goes as t cubed, and at some point it's going to become exponential when the particle becomes relativistic, and it's going to drop like crazy. Okay. And if we just follow this evolution, the amount of dark matter we would have left over at the very end today, when it's very cold, would basically be negligible, nothing. Okay. But the thing that makes this interesting is that this process is going on in the early universe, in particular, both at high temperatures when the kinetic energy of the particles are very high, both these processes go on in our equilibrium in both directions. But at some point, since if we're assuming some heavyish dark matter particle, the process of standard model particles going to the dark matter is going to stop. And that's when things become non-relativistic. When the dark matter becomes non-relativistic, that's when it starts to drop very fast. And at some point, the process from left to right will also stop. Why? Because the universe expands, it dilutes. The dark matter particles don't find each other anymore, and they can't find each other to annihilate and produce a standard model. So they're just the abundance are going to be frozen in. Okay, they're going to freeze out. That we say that they freeze out. The abundance is going to be basically constant in some co-moving volume. So what really happens is that this is what it would be if it remains in thermal equilibrium, but at some point it's going to decouple, these processes will stop, and in which case the abundance is frozen in. Okay. So if the dark matter is in thermal equilibrium until today, its abundance is negligible. But because the universe expands and cools, the dark matter particles will eventually stop annihilating to standard model. And then it decouples, we say it freezes out. So, but if it decouples early, early enough, we'll have a finite abundance. And what you can do is you can basically calculate when this should happen, so when it decouples. And what it obviously has to depend on, it has to depend on the interaction strength. So if you make this interaction strength very, very high, then it's going to remain in thermal equilibrium for much, much longer, and you'll have less and less dark matter. And if its interaction strength is very small, then it's going to decouple early, and you'll have more dark matter. Okay. And this is basically, this variation depends on interaction strength. Which is the cross-section. So actually it's the annihilation rate, so it depends on proportional annihilation rate, so it's the proportional sigma v, actually. Okay. And what you find is that the final abundance is proportional. So the dark matter abundance today is often denoted by omega. The final abundance today is proportional to 1 over the cross-section times velocity. And the way you can calculate this is that you just assume that so when does this decouple? Okay, what's a good criterion for decoupling when this interaction becomes less efficient? So the criterion for decoupling is when the expansion rate in the universe becomes of order the interaction rate. And the expansion rate of the universe is basically given by the Hubble parameter, which tells you how fast the universe expands. And the interaction rate is given by gamma, which is n sigma v. Okay? And the expansion rate depends on temperature, etc. And n, this number abundance, depends on temperature as well. But you can basically equate these two equations and do some math, etc. And I haven't told you what to do, but I don't want to do that in these lectures. But what you basically find is that the final abundance goes as 1 over sigma v, so that if you have larger interaction strengths, the less dark matter you have today. Okay. And the WIMP comes about, the reason WIMPs are interesting and good candidates is because if you have a interaction strength that's of order the weak force, so a picobond cross-section, and you have a particle that's of order the weak scale, then magically, or not magically, you get the right abundance, okay, that we observe. So that's a very interesting observation, which may have been misleading us for a while, because we haven't seen WIMPs, but nevertheless it's an interesting observation. So a particle with mass of order the weak scale, and there's a big approximations, right, of order the weak scale, so GeV to heavier, so a few orders of magnitude of the weak scale, and with interaction strength approximately the weak force. So the standard model weak force. So interactions with W and Z bosons, for example, has the observed dark matter abundance. Okay, the one we observe from cosmological observations, etc. Okay, so if you didn't know about this before, okay, it's sort of a very interesting thing, right? So if you have some particle, that interacts with a weak force, massive order, the weak scale, wow, it has the right relic abundance that we observed today. Maybe total coincidence, but that's what it is. Okay. Good. So okay, let me think for a second. So I want to talk about WIMPs. Okay, I stop at 3:30, right? Yeah. Okay. Okay, so I can do this. Okay, so let's do. So WIMPs are great because of this observation, and the other reason they're great is because we think there should be new physics at the weak scale anyway. Okay, from the Higgs hierarchy problem, for example. Okay. So that's a very strong motivation for there to be new physics at the weak scale, supersymmetry or something. Nathaniel will tell you. Okay, so the fact that you have this observation that a particle with this mass and this interaction strength can give you the right abundance, could be the dark matter. That's very interesting because now you've got two things that point to the weak scale. Okay, so totally independently, dark matter motivates the weak scale, and also the Higgs hierarchy problem motivates the weak scale. Okay, and this observation has motivated a ton of searches over the last few decades. And there's lots of intense effort to look for WIMPs. So independently, so let me just say here, so dark matter points to weak scale. And totally independently, naturalness of the Higgs hierarchy problem points to new physics being at the weak scale. So you could solve two things with one shot, right? You can solve the Higgs hierarchy problem by having new particles at the weak scale, and at the same time, if one of those particles is stable, then from this very generic argument, it's a good dark matter candidate. Of course, the devil's in the details, and whatever you propose, needs to have the right interaction strength, etc. But very generically, that's a very interesting statement, and that has motivated a lot of experimental work. And the experimental work that has been motivated falls into three different categories. So if we have this generic diagram, so we said that, so this is basically the process that led to the freeze out of dark matter. Okay, that gave us the right abundance. But once the dark matter, so the dark matter gets diluted, washes out, and then the universe keeps expanding, it cools, and then we talked about structure formation. So then the dark matter will start forming structure, and it'll again come together in clumps, etc. Okay? And then what happens is that you can again start having large amounts of this process of left to right, where dark matter could again be annihilating 2 standard model particles today in our Milky Way galaxy, for example. So we believe that there's a lot of dark matter in the center of our Milky Way galaxy, so we can take a telescope and look there, and if this WIMP idea is good, we would still expect the dark matter to annihilate 2 standard model particles, and we would expect to see standard model particles in excess of astrophysical expectations. Okay, so we'd expect to see cosmic rays, positrons, antiprotons, of course also electrons, etc. But there's lots of electrons in the galaxy, so we're interested in looking for positrons. We're interested in looking for antiprotons and other things. Okay. And those type of experiments, so you can look for cosmic rays produced by dark matter annihilation in galactic center you can look for them in dwarf galaxies, right? They're dark matter dominated. Dark matter could be annihilating there. You can look for them just in our in the halo of the Milky Way. Look for some diffuse excess. Look for them in galaxy clusters, etc. Okay, and this is called indirect detection, where we try to indirectly detect the presence of dark matter by looking at its annihilation products. And we would look for, as I already mentioned, positrons, antiprotons, photons, and other things. Okay. So if this process, given that this process was going on in the early universe, we expect it to be still going on today under this WIMP hypothesis. Of course, there's many caveats. It might be that this annihilation cross-section is velocity dependent. So it might be that in the early universe, this velocity was because the velocity was much higher in the early universe when it decoupled, that the cross-section was much higher in the early universe than it is today. Okay. So maybe this process is very small today, if the annihilation cross-section depends on v as v squared, if it goes as v squared, for example. Okay. So there's many caveats to, there's no guarantee of seeing anything, but basically this is something that we would could expect. And there's experiments like the Fermi Gamma Ray Space Telescope, AMS 2. I'm sure you've heard in the news that AMS 2 has discovered dark matter, maybe a few times. They have not, but anyway, so there's AMS 2, there's Fermi, and there's atmospheric triangle telescopes, etc. that can look for this. So the other thing I can do then with this is that I can also imagine that given some interaction, that I can also very generically have interaction. So my time always goes from left to right here. Where I just rotate this diagram, I've got an interaction like this. Okay. So then, in this case, what I would do is I would take a detector with lots of standard model particles, nuclei in them, for example, and I would have the dark matter scatter of these nuclei in my detector, and I would look for a nucleus that gets a little kick from the dark matter in our halo. So these are called direct detection experiments. So here you look for dark matter in our halo. You put these detectors usually deep underground to shield them from cosmic rays, because this is a very rare event search, right? You will look for very rare events where the dark matter would induce some little kick, and you don't want to have some radioactive element or radioactive event nearby or some cosmic ray cause the same kind of kick. So you want to shield your detector, make sure the materials that you use are very pure, and put it deep underground to avoid cosmic rays, and then you can look for dark matter like this. And there's of course a big program going on So xenon, 1 ton, n ton, where they have order ton scales of xenon that they put underground in the detector. And similarly in the US, there's going to be an experiment called LZ, and before that it was Lux is still putting out papers, but they're not taking any more data. So LZ is the next big experiment that's going to happen in a mine in the US. And xenon 1 ton, n ton are in Gran Sasso in Italy. So you've got these experiments, and then there's super CDMS, and there's tons of other experiments. Okay, that look for WIMPs. Okay, and then finally, what you can also do is you can hope to produce this at a collider, where you have the standard model particles that you annihilate, 2 dark matter particles, and you produce this dark matter colliders. And since it's hard to see nothing, you have to have some radiation from the initial state, like a gluon or a photon. You can look for mono photon events, mono jet events at the LHC, for example. Or you might, depending on the theory, the dark matter might also be produced in your collider from some cascade, from some other particle that you produce, like gluinos, which then decay down and eventually give you a dark matter particle at the end. So the WIMP has a lot of things to look for. It is motivated by these points here. So it's a great thing to look for, right? And so it has a lot of activity. And that's a good thing. Okay, that's a very good thing. And there's lots of experiments still coming up that will look for it. Okay, and they're going to cover a broad range in masses. Okay, questions on this? Okay, yeah.
What are the physics that actually set up the limits on, for example, on the upper side on the 100 kV?
Good question. So that's my next point. Okay, yeah, let me answer that. Okay. So, again, generically speaking, right, one can try to model building around this. But basically what we have is that this abundance, so let me give this a number. Where are we? So I talked about WIMPs. I guess I made this 4, so anyway. And then let's do this 5. So this is called the unitarity bound. It's related to this. Sorry, just to make sure this doesn't get too cumbersome. All right, so what we have is that the cross-section goes as 1 over sigma v. But there's a maximal possible cross-section that a process can have, which is given by unitarity. And so I didn't see the lecture this morning, but I saw something on the board. So I think this was discussed in the morning, actually. Unitarity bound, is that right? Yeah? Okay, good. So that's fantastic. So we have this. And then generically, we need that the cross-section should be less than 4 pi for a non-relativistic process. And remember, this is non-relativistic. The WIMP freezes out when it's non-relativistic. So we've got sigma v less than 4 pi over v times m chi squared. Okay. So you can check this from the equation this morning. I don't know how it was written. Again, I just saw it far away from the blackboard when I walked in the back at the end. But that's basically a bound on the cross-section. And what we need, right, is that we need this cross-section to be a picobond. Okay, that's the weak force. That's the weak strength. So very generically, interaction strength of picobond are going to give me the correct Rayleigh abundance. Okay, if the cross-section is too, I'll erase the picture. If the cross-section is too small, I'm going to have too much dark matter. Okay, but you can see that there's a maximum, that this depends on the mass. So there's some, as I increase the mass of the dark matter, the bound is going to become smaller and smaller. Okay, and we can just put those numbers in, that basically we need this. So this is needed to get the correct Rayleigh abundance. And what you can do is you can just calculate when this thing basically will be a picobarn. And what you find is that for m chi greater than 100 TeV, you can't make the cross-section large enough. Okay, so that's where that bound comes from. So for thermal dark matter in thermal contact with the early universe and chemical and thermal equilibrium in the early universe, the window that you get is basically up to 100 TeV down to a keV or so. Okay. Okay, so then let me finish some stuff up here. I don't want to say, so I'll just briefly mention this up here. I'm not going to say much about this, just give you a reference. So basically up here, this is, these are big, big objects, 100 solar masses, so we're not talking about fundamental particles at this stage, but people have talked about primordial black holes being of order, tens of solar masses that live up here, and that could be the dark matter. So after LIGO saw, emerging black holes, people thought about, well, what if some of those are actually dark matter, and is that still viable or not? So people talked about having primordial black holes up here. There's lots of constraints on this possibility, but it is an interesting possibility. And a lot of work has gone on in terms of reevaluating these bounds that people have done in the literature in the past. But a lot of, there's constraints all over, turns out, for primordial black holes. And people have reevaluated these given the LIGO observations. But if you want to have some references, there may be a more recent one, but I missed it if there is. So I think this is sort of a review, which is not even that old. And you look at Bernard Carr and company for reviews. So that's an interesting topic, but certainly not one that I'll talk about more. But there are lots of constraints here, and maybe you can't quite make it work with 100% dark matter, but maybe 10%, 1% or so. It really depends on how much you believe some of the constraints. Okay, but it's certainly true that once the dark matter gets very heavy, if it's a primordial black hole or not, doesn't matter. If it's like 1,000 solar masses or 100 solar masses, so these are big, big objects, and those would be around us, go in our halo, and they can go through a star cluster, like a globular cluster or something, and it could disrupt it, and we don't see that. So there's strong constraints on the existence of these things. Then, of course, you also have lensing observations, microlensing, where you would see stars that suddenly brighten if some object moves in front of it, and then it would go back to its normal brightness after the object has moved past. So there's constraints from microlensing and lensing observations. So there's a lot of constraints up there, but it's an interesting thing, I think, to think about as part of the landscape. Okay. Then number 6. So very briefly, let me put another thing here at 7 keV again. Sterile neutrinos have been invoked as dark matter at around the keV scale. They're interesting because of the warm dark matter, because they're way the warm dark matter bound, of course. And we could also, there's also some interesting anomalies on sterile from sterile neutrinos. So in particular, there is an X-ray line. So sterile neutrinos, if they exist, we actually expect that they can decay. So there's a diagram that goes like this. Let me see if I can draw it. US. Okay. So sterile neutrino, nu with subscript S, would mix with the active neutrinos, so the additive from your tau neutrinos. So there's some mixing going on. And the active ones, in principle, you could have a process like this where there's a photon being emitted. This is the W boson, that's the electron, the standard model. And so this is off shell here. But so this, what you have is a neutrino, sterile neutrino decaying to one of our neutrinos and a photon. And you would basically get a photon that has an energy that's half the neutrino mass, sterile neutrino mass. And it's non-relativistic, so it has to be half. And this is around a keV, right, or several keV. So you would expect to see a monoenergetic line of photons coming from, a cluster or galaxies or so. And you can look for those with X-ray instruments. So these are X-rays, right? keV energy photons. So those are X-rays. And there's X-ray observations, quite a few X-ray observations that have seen as some evidence for a line like this. And if you want to see a review, there's a nice review by Kev Wazajian. And he also has talks on this stuff. Okay, so that's another sort of important dark matter candidate, I think, to think about occasionally, that sits around the keV again. Okay. Okay, so now I'm going to focus, not now, I'm going to stop now, but tomorrow I'm going to focus on this mass range here. So I'll start again very briefly with this picture, but what we're basically going to do in these lectures is we're going to focus on below the GV scale. Okay, that's going to be these lectures. Why? Because above a GV, things are well covered by existing searches. We talked a little bit about the WIMP searches. There's lots of searches going on. Also, there's this arrow that stops for WIMPs around a GV. So one of you asked the question, what are these bounds? Okay, I haven't explained to you where the keV boundaries come from on WIMPs. So I'll do that tomorrow, first thing. I'll say why we think WIMPs should be above a GV. But below a GV, then we could have dark matter interacting with a dark sector. Okay, so there's different kinds of searches then we would want to do. And we'll talk about those, both in accelerator-based searches to look for light dark matter below a GV scale, and also in direct detection. Okay. Now there's a whole mass range here, right? So we talked about that below a keV has to be a boson. So you can have, as I already mentioned, you can have axions, axion-like particles, vectors, vector bosons, scalars. That could all be the dark matter candidate by itself. Those are all, if you like, dark sectors, and they all deserve lectures, which you're not going to get from me or anyone else, I think, at this meeting. I think Nathaniel will talk a little bit about axions, but I don't know how much phonology he'll do. But these are all important candidates, and certainly axions are worth their own lectures and searches for these. But instead, what I'll do is I'll focus more on this mass range here, where there's already enough stuff to talk about. Okay, and yeah, I think that's all I want to say today. Yeah. Okay. So we'll start again tomorrow with motivating, in particular, this MAV to GV scale, and even a little bit lower, and then we'll talk about concrete searches that people have proposed and are going to do. Thanks. Questions, I should say. Yeah.
Wasn't there very recently strong evidence for the existence of a sterile neutrino?
Yeah, so that's sort of what I meant with these anomalies. Oh, sorry, I don't know which. So you mean mini boon?
Yes.
That's not this anomaly. Sorry, that's not dark matter.
Yes.
Yeah. So so I won't talk about that at all. We can discuss that offline.
But do people think that there is a sterile neutrino?
There's the cosmologic observations, the astrophysical observations here, which are, I think, very interesting and not conclusive right now. And there's certainly proponents very strongly on one side that they're very, there's strong evidence for something being there. The problem with the keV range and X-rays at a keV is that, if you think about transitions in atom, they tend to be about a keV scale as well. So you have to worry about lines from atomic processes. And so that you always worry about backgrounds. But people have done a very good job or careful job trying to estimate backgrounds, and it doesn't seem to be totally consistent with it. But I'm not an expert on this either. And I think there's proponents on both sides of the debate. And then there's other things, accelerator-based neutrino anomalies, reactor neutrino anomaly, mini-boon, LSND is an old one, where they see oscillations which they're not expecting, which are also very interesting to talk about, which again would be another nice set of lectures, which I'm not going to give. Yeah. Okay. Other questions? Okay, see you tomorrow morning.